Recording is rolling. It is Thursday, February 16th. So we're going to do a bunch of conceptual questions. I gave you guys these conceptual questions here. So there's 4 chapters in the conceptual question book about, got temperature, heat expansion, heat transfer, change of phase, thermodynamics. So that's like the thermodynamic stuff. Okay? There's also 3 chapters on states of matter. We got solids, liquids, and gases. Now that includes things like I think it's some Archimedes principle and Bernoulli principle type stuff in here too. Okay. Before I do that, I want to flash the posters and run screen for the video. Okay, so some of these posters have been hanging from a ceiling for a while. We got temperature scales, got temperature conversions, got the laws of thermodynamics. You guys see all these posters hanging, so you can read this more closely. But we got some thermodynamic cycles. We got Carnot cycle, Rankine cycle. Talked about these back in the last week or two. Stirling engine. Actually, got a Stirling engine here too. Okay, I think I threw this on a cup of hot water the other day. Had that going. This is a little bit different design, but it's the same idea. Engine efficiency. So here's in general how to get it. Here's specifically for say like a Carnot cycle, which is a specific example of that. You guys remember entropy is related to the second law of thermo, right? Entropy always increases in the universe. Right? Thermodynamic processes head one way. Got water, pressure, temperature, phase diagram, solids, liquids, and gas for different temperatures and pressures. Here's a heat curve for water. Now this would be at one specific pressure, like atmospheric pressure. You know it's one atmosphere because oil's at 100 degrees Celsius. Here's different specific heat capacities. Right? You know how much energy does it take to warm up these different materials. Got Newton's law of cooling. So how fast will this mass of water cool off? Well, it depends the temperature difference between this temperature and the environment, right? And also some other things. Okay, and then there's some posters that I've created. Well, I haven't printed these out and made the posters yet, but I have designed these. Okay, so here's some new ones. You guys haven't seen these yet. We got states of matter. So here's going from the coldest on the left to the hottest on the right. Okay, you guys got that? I think I called this something else the other day. Oops, but what's harder than a plasma? And keep heating it up. You get a quark gluon plasma, so like disintegrates the protons and neutrons into like quarks. So there you go. Density. You guys remember density? I told you guys it's sort of like Archimedes in the crown. Density is mass per unit volume. Right? In fact, if you have like a weird shaped object and you throw it in some water, it's going to change its volume by some amount. That's how you can measure the volume. Okay? Throw it on a scale, you get the mass. Divide those two, you get the density. Then you can look up in the table, say, hey, what material is that? Talked about ideal gas law. Pressure times volume equals like the amount of gas usually measured in moles times some constant times the absolute temperature that you have to measure in Kelvin. So we've gone through some of those examples. Archimedes principle. You guys did a whole lab yesterday that involved Archimedes principle, right? So the weight of fluid displaced, which you can further break down into like this, density of the fluid times the volume displaced times the gravity field. That's the upward buoyant force. Okay. Pascal's principle. So here's a hydraulic lift, classic example. Pressure is transmitted undiminished. So if you have different cross-sectional areas, you got different forces. You can lift something very heavy, give you a mechanical advantage. Talk about conservation of flow. So I was really focusing on this one last few days. This is if you have an incompressible fluid like water or some liquid. Okay. Now, if you have something like air going through, which is compressible, you actually have to also include the density of the material because that can matter too, right? Okay. So we got conservation of flow. Now, this is a good setup for the next one, Bernoulli principle. Okay. So Bernoulli principle looks like conservation of energy, but it's in pressure units instead of energy units. Okay. You might have height change, speed changes. This fish swimming through the pipe system feels pressure changes. Okay. You would feel pressure decrease for 2 reasons. One is that the water speeds up. The other is that increased elevation. So the internal pressure changes. We got, okay. I'm going to give you guys an engineering presentation pretty soon in the coming week or so. So you guys haven't seen this yet, but you will. Stress and strain. If you put say like a force in some cross-sectional area, say like a bar or something, okay? How much does it stretch? thermal expansion, I think we talked about this one a little bit. So if you heat something up, it will expand. How much does it expand? I'm showing linear expansion here, although it does expand in all three dimensions. So, right, it's just showing like lengthwise. Okay. I'll tell you guys a bit about I-beams. So, for engineering, make that look like that. We'll talk about concrete. So what's the components of concrete? Yeah, this is all future stuff you guys are going to see in the next week or two, right? Before spring break anyway. Right? Steel reinforced concrete. I guess why that is, what that's about. And the strongest arch you can create, which is if you hang a chain like this, it'll create something called a catenary. Solidify that, turn it upside down. You have catenary arch, which the St. Louis Arch in Missouri is a version of that. All right, so there you go. There's a bunch of posters, some that are hanging from a ceiling, some that I just need to print out and put together. Okay, let's switch over to this Kahoot. Okay, so you guys got your phones out. You guys know, well, starting like end of February, which about a week from now. So coming from the district, they're going to have a cell phone ban. You guys know about this. You guys probably heard in your other classes too. So, I mean, I need you guys to use your cell phones today, but in the future, so you guys have laptops out. That's even better, right? If you have your laptops out, because that's where we're going. You guys know we're headed towards laptops, right? So if you have laptops out, even better, right? Because in the future, when we do Kahoots, you have to do it with a laptop. Right, so I give you guys the conceptual questions. We're starting on all the thermo questions. Now, I'm not going to have you guys turn this page in, but I do need to get you guys a quiz before spring break on all this materials. We're going to look at thermodynamics materials. I still got a few more things I need to teach you guys, but you guys know I like to pick a lot of these conceptual questions for quiz questions. So as long as you're following along, you guys will have some good notes that should help you out on that. All right, anybody else gonna hop on? All right, so I got here. All right, so let's go with again. We're starting with the 4 thermodynamics related chapters. What is heat? Heat. Okay, so we're looking for energy transfer between objects because of a temperature difference. Remember the zero involves as if 2 objects have the same temperature put next to each other. There's going to be no energy transfer. There's no heat transfer. Okay? But if there is a temperature difference, then there's going to be thermal energy going from the hot object to the cold object. If you touch something and it feels hot, it's probably because it's transferring heat energy to you. If you hold an ice cube in your hand and it feels cold, that's because you are transferring heat energy into the ice cube. So heat this is a kind of a definitional thing, but if you paid real close attention to the PowerPoints in the last couple weeks, then yeah, heat is thermal energy transfer. Oh, okay, you need one. Please. Yeah. All right. Next question. Heat is measured in. How do you quantify it? How do you measure this?
Not calories. All of them.
Yeah. So all the above work. I usually talk about joules. Most commonly, that's like base SI units. Calories is also a way to measure energy or heat. Kilocalories is the same thing as food calories. Like if you eat something and says, oh, you know, it's like 100 calories of food calories. That's actually kilocalories. I want to say that's the amount of energy it takes to raise. I think a calorie is like amount of energy to raise temperature water by 1 degree Celsius, something like that. Right. Anyway, so yeah, those are all ways to measure energy in general, including heat, because heat is a transfer of thermal energy. Specific heat capacity related to the amount of internal energy, what? Yeah, there you go. To change the temperature of 1 gram of substance by 1 degree, maybe like 1 degree Celsius or 1 Kelvin. Okay. So you guys know that water has a large heat capacity. What that means is it takes lots and lots of energy to raise the temperature of water versus other materials like metals have low heat capacities. You put a little bit of energy in metals and their temperature fluctuates a lot. So that's a material property. Like water is 4.18 joules per gram Kelvin. Reason an ocean's temperature doesn't vary much from season to season. Ooh. Yeah. Yeah. So the fact that water has such a high heat capacity, and it's really hard to change the temperature of water either way. So anything next to large bodies of water, the climate's usually pretty stable. Okay. Like, hey, how about here in Florida? We're surrounded on 3 sides by water, right? Huge bodies of water. Temperature doesn't fluctuate a whole lot. Oh, the largest extremes in temperature. Where would you expect huge fluctuations in temperature? Okay, so we're looking for middle of a continent. Another way to reason this out was the other three are all similar, like near oceans, near the coast, that's near the oceans, on islands, that's surrounded by ocean. Right? It's like the other three options are all surrounded by huge bodies of water. The middle of a continent, has anybody ever been out to like the Midwest or the plains of the States? Right? Yeah, I remember I took a road trip a few years back before the pandemic, and I was driving through South Dakota, and it was like really hot, like even into the evening, it was like 90 something degrees Fahrenheit. And then just like out of nowhere, this storm like swept through and the plains, and the temperature just like plummeted, like something that you would almost never see in Florida, because right? Like out in the Midwest, they have just crazy weather. The temperature can fluctuate a lot because land has a lower heat capacity than water. Right? So it's easy to change the temperature. During a cold winter, water pipes sometimes burst. Why? Okay, so you guys know when water freezes, it'll expand. Right? Have you guys ever like put a soda in the freezer and forgot about it and come back and it, like explodes? Right? Most materials don't do that. If you go from liquid to solid, most materials get smaller in volume, but water is one of these exceptions there. Yeah, it'll get bigger. Right? So yeah, sometimes that'll happen. Reason you can hold your fingers beside a candle flame without getting hurt. Okay, so those are all true statements. So convection currents travel upward, right? Heat wants to rise. That's this whole the detail about like hold your fingers beside the candle rather than above it. See, if you hold it above it, then air will convect straight towards you, right? Say air is a poor conductor. True. Paul Hewitt mentioned that the other day. Said if this were not true, you would feel cold all the time because like temperature of this room is less than your body temperature. Air convects heat well, also true, but again, that goes straight up rather than to the side. Okay, so those are all true in a certain sense. Heat travels from the sun to Earth by what? How does heat get to us? Yeah, radiation. Remember the vacuum of space? That's the only type of heat transport that can go through the vacuum of space, radiation. Okay. Conduction, you need direct contact with surfaces. Convection, we're talking about fluids, like bulk movement of fluids, right? Because of temperature differences. So the only one that makes sense is radiation. Reason light colored clothes help keep you cool in warm weather. Yeah, reflect a lot of energy. So if you wear dark colors, that'll absorb a lot of energy. If you wear light colors, that'll reflect a lot of energy, a lot of light energy. Which cools at a faster rate? A pot of boiling water or lukewarm water, both left at room temperature? Newton's law of cooling. Yeah. Okay, now why would boiling water cool faster? Now that doesn't mean it is cooler. That just means that the rate change of its temperature it's a faster rate that it'll cool down. Okay? So here's Newton's law of cooling, right? So if you look at boiling water, that could be like here. If you look at lukewarm water, that maybe that's like here. And here's room temperature. Temperature of the environment can be room temperature, like in this room. Okay. So graphically, it has to do with the slope of this line. The question was about the slope of the line, which is actually a calculus question. Okay? So start with the steep slope here, and the slope gets shallower and shallower. That's to say that the rate change of temperature decreases over time, right, as it approaches the environmental temperature. Okay? Or alternatively, you can look at this equation version of it. So the difference in temperature is proportional to the rate of heat exchange. Right? So here's the rate of heat exchange, energy per unit time. Right? That's the rate change of that calculus notation. Right? That's directly proportional to the temperature difference, right? Which would be greater for the boiling water situation compared to the lukewarm water. Cool faster. Newton's law of cooling says that the rate of cooling depends on, oh, and there's the equation I just showed you guys. Yeah, so the temperature difference matters. That's what I just showed you on the equation, which is also that poster over there on the right. Is that right there? Okay. So temperature difference, like the greater the temperature difference, the faster the rate of cooling. Okay. Okay, and these other options just aren't part of that equation. Okay. So there are other parts too, just not the options there. A cup of hot coffee will cool faster if what? Yeah, so black coffee. Will cool faster. Planet Earth loses heat primarily by what? Ooh. Well, it gets to us by radiation. How does it leave the planet? It also has to radiate away, right? So the temperature of Earth is relatively stable. I mean, get real technical. It's been going up a bit over the last few decades, right? That's global warming, part of climate change. But we get energy radiating from the sun, right? And it also leaks by radiation. Like there's not really a convection currents like leaving the Earth because we're surrounded by space. Same problem with conduction. Right? So it's got to be radiation. Condensation. Oh, yeah, going from a gas to a liquid. So for example, water vapor, if it's really humid outside, right, and then there's maybe like a cool night, and the next day there's dew on the grass, right? That's an example of condensation. Right? So what was a vapor cools and turns into a liquid. That's condensation, right? Or maybe you got a glass of tea, and then there's this water that builds up on the side of the glass. That's because there's water in the air, there's humidity, right? And then that humidity hits your glass and cools down and forms condensation. Right? Clouds form when warm air does what? Rises, expands, chills. Is it all of those? Do all those things? Yeah, all the above, and in that order. Right, so warm air will rise. When it rises, guys, where's the pressure greater? Down at sea level or way up in the mountains? The air pressure is greater down near sea level, right? So when it's rising, it's going to less and less pressure. You guys remember from ideal gas law, if something expands, that's so if the pressure drops, okay, if the pressure drops, then the temperature is also going to drop. Right? So it's cooler up there, right? Yeah, right. And then form water droplets, and there you go, you got clouds. When water freezes, for example, forming out snow, so going from a liquid to a solid. Yeah, it's giving off energy. Right? So that's how things cool off, because they're giving away energy. Right? Versus the opposite process, this would be something melting. If the snow melts, it goes back to liquid water. That's because it's absorbing energy, which would be the opposite process. Atmospheric pressure increases. The boiling temperature of a liquid does what? Yeah, would also increase. That's the principle behind a pressure cooker. Right? So water will boil at 100 degrees Celsius at sea level, right? So at 1 atmosphere. Now you can increase that to over 100 degrees Celsius if you pressurize it. So if you have a pressure cooker, right, then you can get the water to say like 150 degrees Celsius or something like that. Right? And the reverse is true with reduced pressure boiling. You guys remember reduced pressure boiling? Like if you put water in a vacuum chamber, then it'll boil at room temperature. So that's like the opposite of this question, like the converse. There you go. Increase the pressure, you will also increase the boiling temperature. When snow forms, the air becomes warmer because why? Yeah, going from a vapor to a solid, right? That's the snow itself is cooling off, but the surrounding environment is therefore gaining that energy, right? It's like a first law of thermo concept, right? So energy output from one mass equals energy input to a different mass. If you want to cook boiled eggs in the mountains, yeah, you just have to boil them for a longer time. And that boiling temperature would be less than 100 degrees Celsius. Maybe it's like 97 degrees Celsius, depending on your elevation. Okay? Now, using a hotter flame is not going to help because the temperature of the water is like once it hits boiling, you turn up the flame, it might boil away faster, but its temperature doesn't change. Right? So that's why it's not the hotter flame. Yeah, just longer time. So I think it's going to do it. The lowest possible temperature in nature. All right, so the best answer is 0 Kelvin. That is equivalent to negative 273.15 something degrees Celsius. Right, so there you go. So 2 of those are all right. Now, 0 degrees Celsius is just the place where water happens to turn from a liquid to a gas, or sorry, a liquid to a solid, or other way around. But Celsius can go negative because remember, Celsius is just a relative scale. So care about this value Celsius or this value Kelvin. So 0 Kelvin is the best answer. Volume of air has 0 degrees Celsius. What if you made that twice as hot? Now what would it be? Twice as hot. Scale up the temperature by a factor of 2. Ooh, yeah, somebody got that. Okay, so let me switch over here and point this one out for you guys. Okay. So 0 degrees Celsius doesn't mean 0 internal temperature. Okay? It means you actually have 273 Kelvin, right? You have all this internal temperature, right? So 0 degrees Celsius corresponds to 32 degrees Fahrenheit or 273 Kelvin. But if I say you scale up something by a factor of 2, you have to think in absolute term, which is a Kelvin scale. So take 273 Kelvin, double it, you get, here, what is that guy calculator here? 273 times 2, that's 546 Kelvin, right? So 546 Kelvin. Then you convert to Celsius, so you subtract off the 273. And that gives you 273 degrees Celsius, right? So 0 degrees Celsius, double the temperature, you actually get 273 degrees Celsius. Because you have to go through Kelvin to scale anything up or down. I've seen Kelvin in a few contexts last couple of weeks. The first law of thermodynamics. Yeah, conservation of energy, which, okay, so energy is conserved. Right? If there's any kind of heat exchange, energy import equals energy export somewhere else. Yeah, so energy is conserved in the universe as a quantity. I can never say that word. Adiabatic processes, thermodynamic processes that involve no mass or heat exchange, think like a closed system, occur where? Yeah, so actually all of those you could simplify as adiabatic processes. So, okay. The greater difference in temperature between input and output reservoir. Ooh, for a heat engine. Hey, remember that Stirling engine? Seep some water through the Stirling engine on it. What's the efficiency? Okay, so would be a greater efficiency for greater temperature difference, okay? Which is actually one of these posters hanging above my head here. Let me find it. Here it is. Here it is right here. Okay. So we got input reservoir and output reservoir. You can say like hot sink and cold sink, sometimes it's called, okay? And a heat engine. So the other day I had a couple of hot water. I threw this on top, gave it a spin, and it just started spinning because it works on a temperature difference. So this engine was like right here. Okay. And the work was like this mechanical energy of this motion, like spinning this thing. Okay. A couple perspectives on efficiency. One is, well, what does this work compared to the input energy? So that works just in general for a heat engine. Okay. Now, if you're talking about the Carnot efficiency specifically, this is the Greek letter eta, it could stand for efficiency. Right? Now, this is an ideal efficiency, like the maximum efficiency you can achieve. Right? You take the ratio of the temperatures and you do 1 minus that. So, and remember, these have to be in Kelvin to make this work. Like, you can't do Fahrenheit or Celsius, it has to be Kelvin. So if this temperature is this temperature, wouldn't this fraction be equal to 1? You guys, what is 1 minus 1? That'd be 0. That's to say, if these were the same temperature, it's not going to run the engine at all. That makes sense, right? The other extreme is you could have your cold sink as like 0 Kelvin and your hot sink is like hot, right? So that would make this ratio approach 0. 1 minus 0 is 1. That's like 100% efficiency. So if your cold sink is 0 Kelvin, then at that point you can have an engine that approaches 100% efficiency. Two identical blocks of iron, one 10 degrees, the other 20 degrees Celsius, put in contact. What if the cooler one cools off even more to 5 degrees and the warm one warms up even more to 25 degrees? Now, you'll never see that in real life because that would be a violation of what? Yeah, so specifically the second law of thermo. The first law, actually, it's okay. If they were identical blocks, identical masses, identical materials, if one cools 5 degrees and the other gains 5 degrees, you would expect that in terms of the first law. So the first law actually checks out. Right? Energy is still conserved. But the second law has to do with a direction of flow of that heat. Like if you put a cold object next to a warm object, it's never going to be the case that the cold object spontaneously gets colder and the warm object spontaneously picks up that thermal energy. Right? You would expect the opposite. You expect them to reach an equilibrium temperature. And the second law says that has to happen. You can also quantify the second law in terms of entropy. Right? There's an equation that goes along with that too. It's heat exchange divided by the temperature it happens at. Okay, so that has to do with the like a time order, like a direction of that heat flow. Running a refrigerator with its door open in a hot room makes the room wet. Will be warmer. We talked about this before. Actually, I told you guys too. I'm going to ask you guys this on the final exam. So I like this question. Now, this is a case where you start off with just a bunch of lukewarm air, just room temperature air, and somehow you make it colder. But that's never going to be a spontaneous process, right? It takes some effort to make that happen. You have to have the fridge plugged in. Right? So you open the fridge door, a bunch of cold air dumps out the front, but don't forget the other part of this process is all the hot air dumping out the back. In fact, because it takes energy to make this process run, the warm air is always going to beat the cold air, and overall it's going to heat up the room. So that's related to the second law of thermo also. Ideal efficiency operating between 2050 Kelvin and 310 Kelvin. Let's do this together. So do 1 minus. You guys got calculators? Do 1 minus. And then do 310 divided by 2050. Now, my screen is showing 0.84878. Okay, so could I call that 85%? 85%? Yeah, there you go. So 85% efficiency. Okay, so that was that Carnot efficiency formula that I showed you guys. All right, back to the podium. We got Ian with the bronze. Nikki with the silver. And the gold. Harry. All right. Okay. And on the other side of the same paper, I've got some more conceptual questions. So let's get a second Kahoot rolling. Let's get pull this up. Okay, wait. All right, well, we got limited time, so looks like here's going to be the winner. It's got to answer at least one question, right? Somebody else wants to hop in here. And so, it says chapter 18 through 20, solids, liquids, gases. Density is defined as what? At mass per unit volume. You guys remember that? Mass per unit volume is density. Could be in a kilogram per cubic meter, possibly. Gram per cubic centimeter, maybe. Saw it yesterday. When a solid block of material is cut in half, what happens to its density? Yeah, it stays the same. Right? So remember, this is an intrinsic property. It doesn't matter how much of the material you have. Mass per unit volume is the same ratio. Less force is required to poke through an eggshell from which side? Less force. Yeah, inside out. So I mean that's probably one reason, like from a biological perspective, that eggs have evolved, right? Because the hatchling is really easy to get out, but whatever predators are trying to get into the egg, it's relatively harder. Right? Now, the engineering principle is if you have an arch is really strong under compression, but then under tension, it breaks apart really easy. An eggshell is kind of like a spherical arch kind of. Which geometrical shape has the least surface area for a given volume? Ooh, how do you minimize the surface area? Yeah. So Paul Hewitt was talking about this one too. Yes, so a sphere has a minimal surface area for some given volume. You can actually prove that with calculus. And actually, I think these are in order. So it goes sphere, then cylinder, then cube, and pyramid would maximize the surface area among those four options. If all dimensions of a house were to double, its floor area would go up by a factor of what? Floor area. Okay, now it would be 4. Now this one, okay. Do you guys remember this scaling right here? Right. Now I'm not showing factor 3 here, but it's the same idea. So anything related to area is going to be that linear factor squared. Floor area is an example of area, right? So if you double the width of a house and double all the other dimensions, it's going to go 2 squared is 4. So it's got to be 4 times. An elephant grows to twice its normal height, its weight will increase by a factor of what? And weight, that's a 3-dimensional concept, right? Weight occupies volume. Remember, the elephant isn't just twice as tall, it's also twice as wide and twice as far back, right? What is factor 2 times a factor of 2 times a factor of 2? Yeah, 8 times. 8 times the volume. If it's the same density, it'll also be 8 times the mass and 8 times the weight. Okay? 8 times. Where is pressure greater? 1 meter beneath Lake Michigan or 1 meter beneath the pond? Yeah, same pressure. Right? That pressure is equal to the density of the fluid times the gravity of the planet times the depth down. Right? So rho GH is the pressure. Water pressure on a submerged object is greatest against which surface? This is related to the direction of buoyant force. If you're floating in a pool, isn't there a net force upward on you? And that's true because there's greater pressure acting from the bottom. From the bottom. Right? So pressure always acts perpendicular to all surfaces, and if some object is submerged, it's in all directions also. But yeah, there's always more pressure from the bottom to the top because the bottom is deeper. So object will always have a buoyant force that's upward. Archimedes' principle says that an object is buoyed up by a force equal to the this is your guys' lab yesterday, right? Archimedes' principle. The weight of the fluid displaced, right? Weight of displaced fluid. So last couple of days, that's been in your notes in the lab that you guys did yesterday. So we talked about that. 2 equal-sized buckets filled to the top with water. One bucket has a piece of wood floating in it. Okay, now why would it have the same weight? Right, now this one I do want to draw up because this one takes some thinking, but okay, so I got a glass of water here, okay, and I got a glass of water that has a piece of wood floating in it. Maybe wood's like floating here. Okay, now remember Archimedes' principle says that the weight of the object, the buoyant force, okay, so buoyant force, weight of the object, this buoyant force is equal to the weight of displaced water. Right? Which would also be the weight of the object, right? So whatever water you're pushing out of the way by having the object float there, you're just replacing one weight with an equivalent weight. So that's why it's the same weight. Okay? It's the same weight. As long as it's the same water level. Right? There's actually more volume if you include the wood block, but same water level, it's the same weight overall. When a boat sails from freshwater to saltwater, now, salt water is more dense than fresh water. You guys remember Archimedes' principle, rho GV? So density, if the density of the fluid goes up, then all else equal, wouldn't the buoyant force go up? And it would push the boat higher up, right? You guys ever heard it's nearly impossible to sink in the Dead Sea? Right? The Dead Sea is extremely salty water. Right? So yeah, huge buoyant force. Right, it'll push you up. Yeah. So it's related to your lab yesterday too. Hydraulic press. Ooh. Okay, so those are all true statements. You guys remember Pascal's principle? So it's not to make this poster, but I'm gonna print this out eventually. And you guys saw this the other day on a PowerPoint. Okay? So different areas, same pressure, you got different forces. You can operate a hydraulic press, hydraulic lift, same idea. Get like a mechanical advantage going. Which side of hydraulic lift is the input force supplied? Do you press down on the small side or press down? How do you lift the car? So the car goes on the large diameter piston, and you press down on the small diameter piston to lift the car, right? Just like the picture showed. Volume of water displaced by 20,000 Newton boat. Wouldn't that have to be the volume of an equivalent weight of water? That's one way of couching Archimedes' principle. Right? 20,000 newtons of water, 20,000 Newton boat. Yeah, there you go. Right. The red one would be true if you're talking about maybe a submarine, but yeah, the blue one is true in general for most boats floating. How high can water be lifted by a vacuum pump? Like, what's the longest straw you can theoretically use? We talked about this one last semester. What's the longest straw on Earth? It has to do with atmospheric pressure. Yeah, 10.3 meters. Okay. So right now, the atmospheric pressure on us, about 100,000 pascals. It's as if we're at the bottom of a 10-meter deep swimming pool, right? We feel that equivalent amount of pressure on us. Squeeze a balloon to half of its original size, what happens to the pressure? So we're looking at half the volume. What happens to the pressure to compensate for an equal temperature? It must double, right? Double the pressure, half the volume, then we're back to like same temperature, same amount of gas. Got it. Standing on the moon, release a balloon filled with helium gas. Now on Earth, the helium balloon would rise, but on the moon, there's no atmosphere, right? So yeah, there you go. The helium balloon has to fall because it has a weight, but there's no buoyant force. There's no buoyant force. It only has a weight. Yeah, that helium balloon's going to fall down to the ground on the moon. When a river narrows, ooh, this sounds like Bernoulli principle or conservation of flow, right? River narrows, the water flows. Faster. Perhaps, well, okay. So that's a conservation of flow from yesterday, last couple of days. On a windy day, atmospheric pressure does what? Here we go. On a windy day, the pressure. You guys remember I blew a stream of air over paper and it vacuumed up the paper. The paper lifted. Same thing there. If you have moving fluids, will decrease pressure. Okay, so here's the answers to the last two questions. If the river narrows, doesn't the water have to speed up because of conservation flow? Area gets smaller, the speed goes up, right? And then this one, so Bernoulli principle, a fast moving fluid will decrease the internal pressure. That's Bernoulli principle. Okay. Okay, we're getting we got right here. All right, last question. The reason a shower curtain will pull to the inside of the bathtub during a shower, you turn on the shower, it's going to vacuum in the shower curtain. Try it. Maybe you've seen this already. Why? Yeah, there's less pressure inside. Again, that's another example of Bernoulli principle. That's Bernoulli principle in action. All right, winner podium. Oh, hey,
Very.
and the gold. Harry. All the gold for Harry. All right, well, that worked perfect because we got 1 minute class left. All right, so hope you guys got all those. Except for questions. Woohoo!